Good afternoon, everyone. We are going to wait, I believe, only 12. So we'll wait till 15:10. Those are like 3 more minutes till we begin. So yeah. Can anyone get me?
Yes.
Yeah.
Okay, so I'm going to kind of say what I said. So I said electric potential tells us how much potential energy a single point charge at a given location will have. Yeah, so we're going to start talking about potential. So we're going to talk about potential electrostatic created by a charge, a unique point charge. So we read, so soit un charge ponctuel Q placé en 0, origine d'une repère orthonorme, or X, Y, Z, cette charge créée à un point M, a champ électrique E. So if we've got a charge at the point O, which is the origin in this repair, this axis, we've got 0, X, Y, and Z. So we've got 3 axes. We've got the X axis, the Y axis, and the Z axis all at 90 degrees of each, all meeting at 90 degrees. This charge creates at a point M a champ electric E. So which I believe we talked about. We talked about how we came up with this guy here, the formula for champ, where U is the vector unitaire de la direction OM. And then in introducing le vector ROM, il vient. So we talked about U. U is the vector unitaire from the direction of O, the point O where the charge is to the point M. So our U is a representation of R, a vector unitaire represented by the vector over the actual quantity, which is R. So we know that R is the distance from O to M, which we can just write as, let me just try to write it. So R is equals to the distance from O, one point charge to the another point, to the other point. Yeah, so we've got OM. So our unit vector U, which is here, is represented by R over R vector over R. So we said if our electric charge is equals to this, where there's U, we simply replace with our actual unit vector. So we know that U is a unit vector in the direction of OM. So we have this is the actual representation of our U. So where there's U, we actually replace with R vector over R. And then we're going to have our shine electric is equals to this guy right here. So we have on sait que le gradient de la fonction scalaire 1 over R avec R is equals to OM. Okay, so now we're going to talk about the gradient of a function scalaire 1 over R. So we move to the how we come up with the gradient of the scalaire 1 over R. So we have a gradient of 1 over R is equals to this. So how we came up with this, simply we differentiated 1 over R. So let me try to do that with you guys. So I have the gradient of 1 over R is simply the differentiation of 1 over R. So if I have 1 over R is the same as R to the power negative 1. Am I correct?
Yeah.
Yeah, so if I have R to the power negative 1, if I differentiate this, I'm going to have negative 1 over r squared. Do you all agree with me?
Yes.
Yes.
Wait, so if I have my differentiation of the scalar 1 over r is equals to this, and then my gradient has direction, so I include my direction, which is in the direction u, or in the direction OM, if you may. I'm going to have this is equals to negative 1 over r squared times r, the vector r, oh my God, okay, yeah, over r. So this is going to be r squared, sorry. So which is what gave us this? Well, we know that our r is equals to OM, because we said if our r is equals to OM, because you know that r is a distance from O to the point M, from one point charge to the other. It's okay for us to also state that our r vector is going to be equals to OM. Which is what we have here. So where E is equals to negative Q, the point charge. Okay, E is originally equals to, our E is equals to, E is equals to this. This is our original E, or this if you express U as it is, which is r vector over r. Then in this case, we introduce the gradient. So gradient of 1 over r is equals to this. So instead of us having this guy here, where there is r over r vector over r to the power 3, we introduce our gradient 1 over r. So we have negative q over 4 pi epsilon 0 gradient 1 over r. And then our actual final champ electric is going to be equals to negative gradient q over 4 pi epsilon r. So what we're trying to do right now is just we're trying to find a relationship between electric champ, which is our E, and our potential, which we're about to do. So this is why we're trying to, we're not complicating, because this is easy stuff, but we're trying to find the relationship between the champ electric and our potential, so that we get our formula for potential. Then after we establish that E is equals to negative grad Q over 4 pi epsilon 0 r, because this r has multiplied with this, so we're going to have negative grad over Q or times Q over 4 pi epsilon 0 times the r, which is here, which is what we have here. So after that, par définition, on appelle potentiel électrostatique créé par la charge ponctuelle Q à la distance r à l'escalier this. So V potentiel is equals to Q over 4 pi epsilon 0 plus a constant, any constant. So this is the formula for V. So V is originally given by V is equals to a point charge over 4 pi epsilon 0 r plus a constant. So you should never forget the constant. So after this, just a minute. Okay, so after we have known this, so we're going to say that if our V is equals to this, and we've established that our E is equals to negative grad Q over this, where there is V, where there is this guy, we can put our V if our constant is equals to 0. So, which is what we have here. Law on a donc, E is equals to negative grad of V. So in this case, our constant is equals to 0. So meaning V is equals to Q over 4 pi epsilon 0 r. and we have our E is equals to this. So where there is this, we put with our V, and we have our E is equals to negative grad of V. I think we talked about this in the introduction. It was one of the expressions, so that's where it comes in from. So we have on law on a donc E champ, which is electric field, is equals to a negative grad V, or V, which is potentiel. We. Are there any questions? Okay, so we move. Yeah, so physiquement, on a aucun moyen pour déterminer les potentiels V. Par contre, on sait mesurer des différents des potentiels entre deux points M1 and M2. So they're saying physically you cannot really determine the average. Moyenne is average potential, but physically you can, physical measurement, you can measure the difference between two points, they different the potential entre 2 points. So the difference in potential between 2 points, yes. So we have M1, we've got the point M1 and M2, which has the potential V1 and V2 respectively. So for us to find the difference between V1 and V2, this is our expression here, which is we just get from, we've said that our V is equals to this. This is in where our constant is equals to 0. So if our V is equals to Q 4 pi epsilon R, V1 minus V2 is just going to be the difference in the distance between R1 and R2. So we're going to have Q open brackets 1 over R1 minus 1 over R2. That's if they try to calculate the difference between the difference in potential between 2 points. Oui, et c'est seulement la différence de potentiel qui a un sens physique, which is what I'm just saying. Dans le SI, on prend aux unités de potentiel les volts. On exprime alors les champs électriques in volts par mètre. So we have V M to the power M squared, M negative squared. Yeah. So our potential is measured in the SI units is volts, and that's why our electric field is measured in measured in volt times meter per meter squared, which is what we have here. So we have our volts.
Hello. I have a question before we go very far. Can you scroll up again? Yes, yeah. On the gradient where you were differentiating, then how did you get rid of that 1 over R squared? Where has it gone, and what was the purpose for us to differentiate?
Differentiate what we're trying to do. I said we're trying to find the relationship between our champ and our potential, which we've started just studying. So we're trying to find the relationship between electric field and the potential. So this is why we have all this. So I say that for us to, okay, sure. Let me just go back to the notes. So down here, okay. So down here, I have, it says, on sait que le gradient de la function scalaire 1R avec R is equals to OM is. So now we're trying to find the gradient of, we've introduced the thing of gradient. So now we're trying to find the gradient of 1 over R, of the scalar function 1 over R. So how do we find the gradient of this scalar function 1 over R? So I said what you have to do is simply just differentiate what you have inside here. So if I differentiate what I have inside here, I'm going to have negative 1 over R squared, n'est-ce pas?
See?
Oui. And then I say the gradient has got direction. Like the direction, the vector, the gradient vector is expressed in direction. So we introduce our direction, which is u. But we've already said that our u is equals to r over r vector over r. So if where there's u here, we replace with our actual vector unit there, what it actually is standing for. We are going to have r 1 over r squared times r, the vector r, so r. And when I multiply this, I'm going to have negative r vector over r 3. So if I have this is this grad 1 over r is equals to negative this over this. So where there is my this in this equation, let me just go back. In this equation, we said we can represent it as this, n'est-ce pas? So we found this, just that it's got a negative. So where there's r this over r 3, we put our gradient 1 over r with the negative. So this is why we have negative q over 4p epsilon 0 grad of 1 over r. And then if I simplify this and multiply it, I'm going to have negative grad q 4 pi epsilon r. Am I clear? And then after I find this, my V comes in. So we're told that potential is equals to Q over 4 pi epsilon R plus a constant. So in this situation, we're going to say that our constant is equals to 0. So meaning our V is just solely equals to Q over 4 pi epsilon R, which we can replace here. So which is what we have here. So we're going to have our relationship between SHA and V, which is E is equal to negative grad of V, which was our sole purpose. We're trying to find the relationship between SHA, how we can express the relationship between SHA and potential, which is what we have here. So we have SHA is equals to negative grad of V. Am I clear?
Yes,
Hello? Okay. Okay, yeah, so we move from here. So I was explaining that physically we do not have the moyenne, maybe they tell you to find the potential moyenne, but you can measure, physically you can measure the difference between the difference in potential between 2 points, which is what I was saying here. Same, we're still saying that our constant is equals to 0 in this case. So we're going to have V1 more V2 at M1 and M2 respectively. So we're going to have Q is equals to, we're just going to consider the difference in the length, or the R1 and R2, because R is usually the distance from one point charge to the other point charge. So here we have 1 over R1 minus 1 over R2 respectively, because this is V1 minus V2. Which is what I was saying. And then its potential is measured in volts. So our electric shunt is going to be measured in volt per meter squared, which is, those are the SI units for shunt. So yeah. So we move to, are there any other questions? Okay, so we move to potentiel, electrostatic, clear bound, distribution, décharge, discrete. So we have Swann's ensemble décharge punctuel Q1, Q2, Q3 up to Qn. So we've got a set of charges Q1, Q2, Q3 up to Qn. They create at the same point M the champ electric E1, E2 up to En. So each charge produces a certain electric field which is being produced at M. So on définit le potentiel électrostatique créé à un point M par l'ensemble de la distribution par V is equals to 1 over 4 pi epsilon 0. This is the summation, I believe, it's the summation from the first charge to the last charge, which is I is equals to N, Q I over Ri plus the constant. So this is just our same, we're trying to find the potential of all the charges, all the charges. So we're going to have potential is equals to this, the same expression. We add the summation of all the charges. So we're going to have this I, Ri plus the constant, which is what we have here. So our expression for V is equals to this. So here we're just, let me go to the actual expression. So V is equals to this plus constant. So we just introduce the summation Q over R plus the constant. So that is what we have there. And then what's this remark? In general, si il n'y a pas de charge à l'infini, on prend par conversion constant is equals to 0, CV is equals to 0 à l'infini. So this is what I was saying. Usually the constant, if there is no charges at infinity, on prime par conversion constant is equals to 0. So usually, like on the exercise that we had the other time, we're trying to find the electric field at a point, maybe in the sphere or outside the sphere. So if I have a field that is maybe, okay, we have a field à l'infini. We're saying, see, if we do not have charges à l'infini, on prend par conversion constant is equals to 0. If we have swap V is equals to 0 à l'infini. So V is equals to 0 at infinity. So our potential is equals to 0 if we have charges on infinity. So to say, so if we have, let me try to draw, if I have a sphere, comme ça, and then maybe I'm told to find the potential at a point here, or at the point here, or at a point infini, any point, a point l'infini. I don't know how to, to put it on, to draw it, but at the point infinity. So our potential is going to be equals to 0. So at l'infini, our potential is going to be equals to 0. So we have, we have potentiel électrostatique créé par une distribution continuous de charge. So we have chaque élément de la distribution possède une charge quasi-punctuelle de valeur. So quasi-punctual is like the Q. It's not Q, but it's almost Q. So which is what we have here. So we have the Q. Chaque élément de la distribution possède une charge quasi-punctuelle de valeur. The Q is equals to this for one distribution volumic, or the Q is equals to this for one distribution in surface, or the Q is equals to this for one distribution linear. I think we discussed about this. So so for we have elements of the distribution carrying this certain amount of charges. The Q is equals to this for distribution volumic, the Q is equals to this for distribution surfacic, and the Q is equals to this for distribution linear, meaning our potential respectively at this point is going to be V is equals to 1 over 4 pi epsilon 0. This representing that we're dealing with volume, we're integrating volume. So we're going to have dq we're going to have dq here. So where there's dq, we put our rho dv, Then I hope you know where the dq is coming from. So it's like where we have, let me try to write. So we have our v, our v is equals to is equals to 1 over 4 pi epsilon 0 q over r. This is our expression for potential. So we know that when we're trying to calculate dv, we're going to have is equals to dq su 4 pi epsilon 0. Yes. So now we're trying to calculate the potential at dq, at each dq. So if we want to calculate the total potential at this dq, at this petit charge, we're going to integrate for us to have v. So we're going to have v, say egal 1 so 4, because this is a constant, we have 4 pi epsilon 0. So since this is in distribution volumic, we're going to integrate it 3 times. So we're going to show that we are trying to find the volumic. Oh, it's a distribution volumic. Yeah, which is that rho, where there's dq, which is equals to rho dv, we just replace with our rho dv. Yeah, so this is where this is coming from, plus a constant. Don't forget that our expression for v has a constant v, so that is what we're going to have. And then the same for distribution surfacic, and the same for distribution linearic, which is what they were having here. So for volumic, they have the 3 integrals, and for surfacic, they have the 2 to show that it's surfacic. And for the linearic, they have the 1. Yeah, so that's that. So we go on top. Yes, which is that. So we have this for the where v is equals to this for the linéaire. S'il n'y a pas de charge à l'infini, on prendra the constant is equals to 0, which is what I'm just saying. And then we have surface equipotentiel. So a surface equipotentiel is simply any surface over which the potential is constant is called an equipotential surface. So an equipotential surface is a surface over which the potential is a constant. So in other words, the potential difference between any 2 points on that surface is the potential difference between any 2 points on an equipotential surface is equals to 0. So the potential difference between any 2 point surface on an any 2 points on an equipotential surface is 0. And that's a surface equipotential. So the potential is equal to a constant, or the difference between any 2 points on that surface is going to give us 0, which is what they are saying here. So we have v at the point v, x, y, and z in the x, y, z plane is equal to a constant v. Potential is equal to a constant. Yeah, so we have ligne des champs électriques. So for electric field, electric field is equals to 0 in a surface that is equipotential. sur ligne de champ électrique, on appelle toute coupe tangente en chacun de ces points au vecteur champ électrique en 0 point. Sur une ligne de champ I et tangente à la ligne, this champ vectoriel dl is equal to 0 for un déplacement dl sur la ligne. So let me try to explain what they mean here. So the champ is going to be equals to 0 in that free charges can, in a, what can I say? Let me try to look for the words. Okay, the lines, electric field is going to be equals to 0. Electric field times the dl, or vectorial dl, is going to be equals to 0. That's a potential electrostatic clear bound distribution continuity charge. On that surface, the champ and the dl or the ds or the dv is going to be equals to 0. Simply, yeah. Then we have equation de Poisson, which is our new expression. So we have equation de Poisson. So the Poisson equation states that the Laplacian of electric potential at the point is equal to the ratio of the volume charge density to the absolute permittivity. So we're going to talk about what I'm just from saying. So if we have on a vu que le théorème de Gauss s'est traduit localement par, so we have the divergence of E is equals to this, which we discussed in our last lesson. So if we have the divergence of E is equals to rho over the permittivity, we have E is equals to gradient of V. So we've established that our E is equals to a gradient of V. So where there's E, we replace with our gradient of V for us to get the equation de Poisson. So where there's E, we replace with our gradient of V. So we're going to have divergence of gradient of V is equals to rho over epsilon 0. Sorry, that was cut out. So yeah, so I'm going to have where our divergence, this is going to be equals to this. So let me draw. So I say that from our divergence or equivalent de Gauss, we have divergence is equals to of negative. Where there's E, we replace with our negative grad. So grad is equals to, okay, grad V is equals to this constant over epsilon 0. So here what happened is that where there's the negative, they just divided it and it went the other side. So where there's rho epsilon as 0, they replaced with Laplacian. So the triangle and the V is a representation of the Laplacian. So we have divergence of the gradient of V is equals to Laplacian. This is another formula in which we can try to find our V if we're given the divergence in the gradient. So Laplacian de V is equals to this. Laplacian de V is equals to change the partial differentiation squared V over this same here in coordinate Cartesian. So you're supposed to know that the Laplacian in coordinate Cartesian is given by this expression right here. And then the Laplacian is this constant that's being replaced by this, the rho over epsilon 0, the negative rho over epsilon 0, because this gradient has been divided this side. So in coordinate Cartesian, the Laplacian is equals to this. And then this is the final equation de Poisson, which is gotten from, so if we have our constant here, so we have dv, we have, what's this? The triangle V is equals to negative rho over this epsilon. So when we take this negative epsilon over negative rho over epsilon 0 to the other side, we have dv plus rho epsilon 0 is equals to 0, which is our actual equation de Poisson. So if they tell you using the equation de Poisson, you calculate the potential, you know which one is the equation de Poisson and where it's from. So we have this as the equation de Poisson. And yeah, so we have, now we're going to talk about conductors. Yeah, so a conductor, I'm sure we all know what a conductor is. We did this in physics. Conductors in equilibrium, electrostatic. So what's a conductor in equilibrium? So a conductor is obviously, yeah, we know what conductors are. So we're going to read conductors in equilibrium. A conductor, un conductor contient des nombres électrons libres animés d'un mouvement désordonné. On dit qu'un conducteur est en équilibre lorsque les charges libres qu'il contient sont toutes au repos. So a conductor has a number of free electrons. So we call it a conductor in equilibrium if the charges, the free electrons are at rest. So there's no movement of electrons or charges, and we call it a conductor in equilibrium. So une action extérieure peut provoquer la mise en mouvement de ces charges, ce qui donne lieu à un current electric. So unless there's an action exterior that can provoke the movement of the charges, so this is an exterior movement, a provocation, an exterior that can provoke the movement of the charges or the electrons in that conductor. But otherwise, a conductor in equilibrium is we call it a conductor in equilibrium if the charges or the electrons in it, the free electrons, I mean, are at rest. That's what we have here, there. So we have a propriété d'une conductor in equilibrium. We have champ in electricity. So we're going to talk about the properties of a conductor in equilibrium. So the electric field in a conductor in equilibrium is equals to 0. So if we've got a sphere and the electrons inside or the charges in it are at rest, the champ electric is going to be equals to 0, in that if we've got charges inside a sphere, let's say this sphere qualifies to be a conductor. So we have a sphere and then there are charges inside. So charges produced by the conductors inside are going to cancel each other out. So the charges, the positive charges are going to be producing forces and electric field in different directions. Some are going in, some are coming out. So the net champ produced inside that sphere is going to be equals to 0. So properties for a conductor in equilibrium, the champ electric is going to be equals to 0. So yeah, and then the potential, V is equals to a constant because the E, the champ is equals to 0. From our formula, we can just integrate. If our E is equals to 0, our V is going to be equals to a constant. And then we're going to have the density volumic décharge. The density volumic décharge, our rho is going to be equals to 0 because our charges, our density volumic décharge equal equation de Poisson. So we're going to have divergence of E is equals to rho over epsilon 0. So if we have divergence is equals to 0, or we've got our champ, which is equals to 0. So we have our champ equals to 0 here is equals to rho over epsilon 0. Our rho is going to be equals to 0 when we do up the cross multiplication. So we're going to have this over this. When we do this, we're going to have our rho is equals to 0. So yeah, that's it about potential and conductors in equilibrium. So we're going to finish up the exercise that we did the last time while we were calculating the E. We just calculated the E, I believe. Yeah, so we just calculated the E the last time. So now I think since we've done a bit about potential, we can be able to calculate the V. So let me try to, do you remember the exercise, or I go back and share the screen for the exercise?
Share the screen.
You can just share, I think.
Okay, so I believe it was here. Okay, so here we have it. So we have exercise 2 and exercise 3. So we have this soit une couche sphérique uniforme des rayons A portant une charge Q. Utilisant le théorème de Gauss, calculer E et V à l'intérieur et à l'extérieur de la sphère. So we calculated our E the last time. So now we're going to calculate the V. So this is how our questions come. So we're trying, using the theorem de Gauss, calculate the electric charge and the potential at the interior and exterior de la sphere. So we're going to start with exercise 2, which is this guy here, this sphere right here. So we go to our today. So we're going to have, last time we calculated that in the interior, so we have a charge like this. Let me just draw it. We've got the sphere. So we've got a sphere. And then we have charges outside. Okay, yeah, so we have charges outside, basically. Yeah, we have something like this. And then I've been given that from the center and we've been given the radius, which is equals to A. And then we were taught to calculate the charge outside or exterior at a certain point. So we calculated the charge inside and the charge outside. So exercise 2, we're now going to calculate the V. So we're going to use our formula for charge, which we just did today. We're going to use charge is equals to the negative grad of V for us to calculate our potential. So how did we come up with the potential? So when R is less than A, which is in the interior, when R is less than A, let me use the spotlight. So when R is less than A, which is in the interior of the sphere, we said that our E is going to be 0. That's what we discussed last time. So we say that in here, because there's no charge, our E is going to be equals to 0 because our charge is 0 inside here. And then if our E is equals to 0, our grad V, so we have this. We have E is equals to E is equals to negative grad of V. We have negative grad V. So if our E is equals to 0, we have our E equals to 0. Our V can be calculated by what do you call it? Integrating. So we have our. I'm going to finish. Okay, so we have our R. We've got our A. We've got our D. Sorry, writing is very hard here. So we've got our negative grad V. So for us to have our V, simply we're just going to integrate both sides. So if we integrate any constant, So if we integrate and any constant, we're going to have, if we integrate 1, we're going to have is equals to 0 plus a constant. If we integrate anything, we're going to have 0. We're going to have the integration plus a constant. So here we simply just integrated both sides. So if we integrate this side, we're going to remain with a constant, and we integrate, sorry, and if we integrate this other side, we're going to have v. We're going to remain with v. So we're going to have 0 is equals to, so if we integrate this side, we're going to have v, negative v, if you may, we're going to have negative v is equals to a constant, which we're going to get from integration of any number or constant. So we're going to have the constant, constant is equals to v. Yeah, so this is what we have here. So which we're going to have v is equals to a constant. V is equals to any constant. Yeah, which is what we have here. So our e, if our e is equals to 0, we're going to integrate this, and if we integrate this, we're going to have v is equals to a constant. So v is a constant, and we name that constant a. So v is equals to a constant, which is equals to a. So that is what we found for the first one, where our champ electric is equals to 0. So yeah, which is what I have there. That's in the interior, because our R is less than A. So our interior, le champ is equals to 0, and our potential is a constant. So for our exterior, we have R is greater than A. So for the exterior, I want you guys to really follow me. So we're going to have our exterior was, our value for the exterior was equals to, was equals to this. So our E was equals to 1 over 4 pi epsilon 0 q over r squared in the direction ER. This was our champ, our exterior. So we're going to use the same E is equals to negative gradient of V. So this is a sphere, so we're going to use coordinate spheric. So the expressions, I remember that I did in the introduction, for our formula for gradient in reverse spheric is this guy right here. So we're going to have this grad V is equals to dV over dr in the direction ER plus 1 over r sine theta, dV over the phi in the direction E phi plus 1 over r dV d theta in the direction E theta. So this is my gradient V in the coordinate sphere, because we're dealing with a sphere. And then, so what I'm going to have is that my champ is in the direction ER. So meaning my champ is in the direction ER. So where there's ER, this is what we have. So I have champ is equals to this, plus I do not have anything in the direction E theta, and I do not have anything in the direction E phi. So we're going to have champ is equals to 1 over 4p epsilon 0 q over r squared ER plus 0 E theta plus 0 E phi. So from here, what we're going to establish now is going to try to establish a relationship between dV and our champ. So we're going to have, after I have this, I'm going to have, let me draw. I'm going to have my change in dv over the phi is going to be equals to 0, like here we mentioned, so they have nothing in the phi. My change in dv over d theta, my partial change in dv over d theta is going to be 0. And then my dv over dr, I have something in the direction of er. So I'm going to have dv. So don't forget I said my E is equals to a negative of grad V. So I have negative of grad V. So my grad V, I've said in the direction dv dr, we have something. So I'm going to have dv dr is equals to this guy here. So in the direction dv, this, so let's just say this is equals to E. As we've established, negative this, I mean. So this is where this expression is coming from. So I'm going to have dv over, sorry, I'm going to have dv over dr is equals to negative 1 over 4 pi epsilon 0 q r squared. So I've established that my E is equals to this, my E is equals to this, so meaning my E is equals to my E, which is 1 over 4 pi epsilon 0 q over r squared is going to be equals to dv over dr er. Okay, so we have the direction er there, and we have also our direction er here. So this and this will cancel. So our E, I mean, so our E is equals to negative V. So we're going to have negative here. So if we do our math, we're going to have dV over dr is equals to negative 1 over 4 pi epsilon 0 r squared q over q, which is what I have here.
I think it will catch better
Which is what I have. Which is what I have here. So for me to have my dV, for me to get my potential, I just make dV the subscript formula. So I'm going to have this guy multiply this, and yeah, have this. I'm going to cross multiply here. Sorry, let me draw. So I'm going to have this. This, for me to have my dV, I'm going to end up with having my dV is equals to this. If I do my math, my dV is going to give me equals to this. And then for me to find my V, I just have to integrate my dV. So if I integrate my dV, I'm going to have this is equals to V, which is V is equals to negative Q 4 pi F integral 1 over R times dr. And then if I integrate 1 over R squared R, I'm going to have this guy here. This guy, sorry. So if I integrate this guy here, I'm going to have this guy plus a constant. So which is what I'm going to have here. So I'm going to have then this negative will multiply with this negative. So my final expression is going to be Q over 4 pi epsilon 0 1 over R plus the constant which will give by the name of B. So if there are any questions, I can gladly repeat what I just said. You can ask. Are there any questions, any queries?
Yeah, I have a question. What are we finding first?
We're trying to calculate our V, our potential. Okay, so I'll repeat what I'm just from explaining. So I started from, so we're trying to calculate our V. So we had our E. So for the first one, our E was equals to 0 at interior. Our E was equals to 0. Our E was equals to 0. And at exterior, our E was equals to 1 over 4 pi epsilon 0 Q over R squared. Q over R squared in the direction ER. So this is what we had. So for the first one, I said for us to calculate the V at interior, we found that our shan was equals to 0. So what we simply do is just we integrate this side and we integrate this side. So we're going to integrate, for us to have V, we're going to integrate this side and then we're going to integrate this side. And then we know when we integrate anything, we have the integral plus a constant. So if we integrate 0, we're going to have a 0 plus a constant, which is what we're going to have here. So if we integrate this side, we're going to have V. So our V is going to be equals to a constant. And that constant is going to be given the name A. So we've named the constant is going to be A. Then our exterior, we're going to have our E is equals to this. So we use our E. That's why we're trying to find the relationship between E and V. So we're going to our exterior where R is greater than A. Our shan, we said our shan is equals to, what's this? Okay, yeah, we said our shan is equals to this guy in the direction ER. So now we're dealing with spheric. So when the coordinate spheric, so we're going to have our E is equals to 1 over 4 pi epsilon 0 R squared in the direction ER plus 0, because we have nothing in the E theta direction, plus 0 in the E phi direction. So we have E is equals to this in the ER direction. So we're now going to introduce the gradient in the coordinate spheric. So we have our gradient in the coordinate spheric. Our expression for gradient in the coordinate spheric is equals to this. So from our E, we have our change, our dv d theta, our dv d phi is equals to 0. Our dv d theta is equals to 0 because we have nothing in that direction. But our dv de dr, our dv dr, we have something in that direction. So which is what we're going to work on. So our dv dr is going to be equals to negative 1 over 4 pi epsilon 0 qr squared in the direction ER and in the direction ER respectively. So our ER directions will cancel. Our directions will cancel. Here we have ER, which can be here, and here we have ER. So this negative is coming from the fact that we have E. We have E, our E is equals to negative of gradient. Our E is equals to negative of gradient. of gradient V. So we have this. So this negative, this is from here. So this is what's supposed, because our gradient is equals to this, and we've established that our E is equals to negative of grad V. So this is equals to this, but since we're trying to find the V, we just divide by negative both sides, where we have this having the negative. And then for us to find dV, we now differentiate. So we make dV the subdivisional formula. So by making dV the subdivisional formula, we're going to have this is equals to this. We're going to have this as our dV. So for us to get V now, we have to integrate both sides. So if I integrate this side and I integrate this side, I'm just going to integrate, I'm not going to integrate the constant. So the Q divided by 4 pi epsilon 0 are going to come this side. And then we're going to integrate 1 over r squared in the direction dr. And then I said the integration of 1 over r squared, or maybe we do the integration. The integration of 1 over r squared is equals to r negative 2. And then we know our integration. Integration is plus 1. You add plus 1 divided by negative 1, which is going to give us this. So after this, I put it, I go ahead and multiply. So I'm going to have, where there's my integral of this, which I found is equals to this plus a constant, is what I'm going to put. So the negative and this negative will cancel each other, and then I'll have Q over 4 pi epsilon 0, this plus a constant, which is given by the, which we represented by B. We move on. Hello, we move on, or the people questions.
Yes.
We move on.
Oui.
So our potential is equals to Q over 4 pi E epsilon R plus a constant, which is B. So have you guys done limits in analysis?
No.
Okay, so this will be tricky to explain. So we have to, the limits, conditional limits, so we're not done because we have to find our B. We have to find what B is as a constant and what A is. That's why we have to use in the limits. But let's try to find the E for the other question, for question 3, and then we'll come back to the limits. So for exercise 3, we said that our potential, we found our E was equals to, our E a la R is greater than A a la exterior. Our E was equals to, our E was equals to rho A cubed over 3 epsilon 0 r squared. This was our E a la exterior. So we're now trying to find the V. So we're going to use the same formula. We're going to use E is equals to negative grad of V. So at the exterior, we're going to use the same thing. It's a sphere, so we're going to get the gradient in coordinate spheric. So we're going to have gradient is equals to dV, change in dV, dr in the direction ER plus 1 over r sine theta, change in V over change in phi in the direction of phi plus 1 over r dV d theta in the direction E theta. So this was in the direction ER. This was in the direction ER. So again, we have nothing in this direction. We have nothing in this direction from our champ. So our champ class, we have nothing in the theta direction, I have nothing in the phi direction. So I'm just going to do with the change in ER. So we have change in dV over dr. So we're going to say this is equals to a negative of dV over dr in the direction ER. So we have this. So this and this can go. So now we're going to establish dV. So we're going to make dV the subject of formula. So we can just simply divide this by -1, first off, by -1. This side as well by -1. So we're going to have what we have here. So we have dV dr is equals to this. And then our dV, when we make dV the subject of the formula change in V, we're going to have this. And then when we integrate this to find our actual V, we're going to differentiate, we're going to integrate it. So the constants are going to be here, and then we're going to integrate it by this. And then the integration of this over this is equals to, the integration of 1 over R is the same as we had just from calculating in the other exercise. So the integration is equals to -1 over R. So if I replace this here, my negatives are going to cancel and I'm going to remain with this plus a constant V from our integration. So that's how you get the V, I mean the potential. That's how I calculate the potential. So yeah. And then for for this is a la exterior because our R was greater than A. So this is a la exterior. So we're going to calculate the one for a la interior. So a la interior, we found that our E was equal to rho R over 3 epsilon 0 in the direction ER. So I'm going to do the same thing. So I'm going to do the same thing. So this will be equals to negative gradient, but our gradient in this case is just going to be dV over dr, because we have nothing in the theta direction, we have nothing in the phi direction. So we're going to have this ER. And then we're going to do the same thing. So we're going to cancel our E, and our E is going to cancel. Then we divide the negative. We're going to have this, what we have here. And then if we have our dV, we're going to change the subject formula. We're going to have dV as a subject formula. So we're going to have dV is equals to this in the direction dr with the direction dr. The expressed in dr, I mean. Then we're going to have, if we integrate, we're going to have dV is equals to the integral of this, but this is a constant. So we bring it the other direction. So we're going to have this, which is what we have here. So we're going to have negative rho 3 epsilon 0 integral R dr. And then if we integrate R with respect to dr, if we integrate R with respect to R, we're going to have R squared. So integral of R with respect to R is going to be R squared. R squared over that's the integral of this guy here. What's going to give us plus a constant. Let's not flip the constant. So we're going to have plus a constant, which is what we have here. So this, we're going to multiply it to our actual V. So we're going to have this V is equals to negative rho R squared over 6 epsilon 0 plus A, because this 3 will multiply with this 2, and the R squared over epsilon 0 plus our constant, which we've named as A. Are there any questions? Are there any questions, any queries, any, yeah. Hello,
We proceed.
c'est tout.
Oui, c'est tout, c'est tout.
Oh, okay, d'accord. So since you guys haven't done limits, I don't really know how to explain this, but we have to find the actual value of A and the actual value of our constants using limits, which is what we'll be doing, but that will be a bit confusing because we haven't done limits. So we'll save it for another day. But that's how you calculate your potential and how you go about it. So are there any questions from today's lesson?
Oh, just like you had recommended some YouTube channels the previous lesson, are there also some that you can send us for today's lessons?
Yeah, I can try to look for some so that you guys go through.
Okay, that will be really helpful.
Yes, and so can you kindly make a summary of the E and the V, or on question 3 and 2, like the differences, how they are differing from the internal and the external.
So for exercise 2, we had a sphere like this. We had the charges outside. We had the charges outside, the positive charges outside, and then we're told to calculate the electric shunt in the inside of this sphere and at the exterior. So yesterday we talked about this, and then we said that in the inside, our E is going to be equals to 0. And in the outside, our E is going to be equals to this guy here. In this direction. That is what we said. So now today we're going to calculate the potential. And then we have the relationship between champ and potential, which we've established today is equals to E is equals to negative gradient of V. So this formula is done that has helped us to actually calculate our V for an exterior and an interior for all the surfaces, which is what we have been doing here. Yeah, which we have been doing. So for here, we said that our E was equals to 0. So we replaced here with 0. We integrated both sides. We had a constant this side, and here we had V. So our V was going to be equals to a constant. And then we've given the constant. We've replaced the constant by a constant A. And then the same thing for the other guy. We have our exterior. We have R is greater than A. But we have our champ. Our champ is equals to this, but we're dealing with, we're in coordinate spheric because we're dealing with a sphere. So we're going to have in the direction R, in the direction theta, and in the direction phi. So our gradient in coordinate spheric, we already discussed that in the first lesson. Our gradient is equals to this. It's our expression for gradient. You're supposed to know it, at least if you do not know how they derive it, know it back here, because they won't really ask you how to derive it. They will just tell you to use it, like how you need to use it now. So we have this gradient is equals to this. And since our E is equal to negative of gradient, this is what we have here. So this is our E is negative, E is equals to negative of the gradient, and our gradient is equals to this. So we have negative of this is equals to our champ, which is our E that we established. And then we find dV, we make dV the subject of formula, and then we integrate it. And then we have our expression of V. And then we do the same with the question 3.
Okay, yes, from what I've seen, it's like whenever we had the charge as 0, but still we could have the potential, right? So does it mean the potential is not affected even if the charge is 0?
Now, if the charge is 0, the potential is going to be a constant.
Okay.
The champ, the electric field inside maybe a sphere is equals to 0, the potential inside the sphere is going to be equals to a constant.
Okay, thanks.
Okay. So I think today we'll end here, and then next week we'll continue with our lesson. Yeah. So since there are no more questions, I believe today we've moved from the Gauss law. We've talked about the potential, we've talked about conductors, and we've talked about the equation de Poisson. And next week we're going to continue from there. We've talked about potential, we've talked about Laplacian, we've talked about the equation de Poisson, we've talked about the Laplacian in coordinate Cartesian. We've also talked about conductors in equilibrium. So conductors in equilibrium and how they behave and their characteristics, which we mentioned here. So we said the champ is, if the champ is equals to 0, our volume is equals to a constant. We said our rho is going to be equals to 0. Our density volumic, the charges is going to be equals to 0 because our champ is equals to 0. And yeah, we did an exercise or two on volume, on potential. Yeah, so I hope you have a blessed day and shalom.
Just before we close, I think you need to help us by maybe summarizing the formulas, those ones which are more important, like the most used formulas, because the drivings, somehow.
Okay. So the lessons really, they're just for you to know where the formulas are coming from, but you need to know where the equation de Poisson comes from, where the divergence E rho is equal to epsilon 0 comes from. But I'll try to summarize the important formulas rather. So I think all of them are important, not the derivatives, but the actual formulas are important. And I'll try to send them in the group and we'll see how we move from there.
D'accord, thanks.
All of these are related, so okay, yeah. Most of them are related because if you have this, it will give you this if you just rearrange them in some way. So yeah, but I'll try to do that. Okay, so have a good day and shalom.